everyone, and welcome back with another new section in the subject, that is fundamentals of particle and fluid solid processing. Today we will be discussing on transport of fluid solid systems. Now till now we have seen several aspects of these particles, that is starting from its size determination, and then we have seen its separation, how particle moves in a fluid or how a fluid moves around a particle. We have seen how sediments can be separated, or say the particle fluids can be separated by fluidization, by sedimentation, by filtration. Also we have seen how to reduce the particle sizes. We have seen how to enlarge that. Now today we will see that how the particles and the solids, the fluids, how do we transport them, or what are the transport fundamentals, the transport mechanism when we try to move particle from one place to other place. Now as itself just moving the solids or flowing solids, we have seen it's difficult due to its characteristics. So it is typically mixed with another fluid, and now that fluid can be of liquid or can be of gaseous state. Mostly in practice for the gaseous phase, it is the air that is used in order to transport the particles from one place to other, and such scenarios called the pneumatic conveying or the pneumatic transport of the particle. The other one, when the liquid phase is involved in order to move these particles from one place to other, that is the main component becomes the water. That water is typically or most widely used liquid phase in the liquid and the solid system transport. So and this second one, that is when it is involved with water, that kind of transport we say the slurry transport. Now instead of water, that can be of other liquid. Now typically, as I said, mostly used liquid component is the water. Now today we will focus on this slurry transport, and then we will move on to the pneumatic transport at a later stage. So which means the transport of fluid solid systems, we basically have divided in two components further. One, when the fluid is gas, that is the pneumatic conveying, and when the fluid is liquid, we call the slurry transport. So in slurry transport, the slurry, or we can say that this is a mixture of the liquid and the solid particles, and this is the broad definition of a slurry. And when this is highly concentrated by the fine particulate materials, this slurry we call as sludge. Now it has widespread applications, it has immense applications in various areas of mineral transport. For example, say the coal, phosphate, and all these industries also, when they try to transport these coal particles from one place to the other, this kind of slurry transport is useful. Also the handling of slurry is involved when there are the applications of dredging of slants or slits for maintaining the waterways, and there also this sand and water mixture, it basically we can call that it is a slurry of sand which has to be handled. So it has several applications. Now as I say, mostly the liquid phase is water in slurry transport, but there are examples or evidences that the slurries can be of coal oil or coal methanol fuel. This kind of slurries are also there in application, but mostly it is the water that happens to be the liquid phase. Now, when we transport the slurry or transport the particles in terms of slurry, now there the fluid property typically changes. That fluid property means the water property or the original fluid property without the particles. It has its own characteristics, but when certain concentration of slurry is mixed or certain concentration of fine particulate solids are mixed within it, then its characteristics also changes. And in order to calculate or estimate the pressure drop when it flows through pipe, we need a one common parameter or the vital parameter, that what is the density of the slurry. Now, this density can be obtained in couple of forms. So, typically it is used as the slurry or the mixture density, which is calculated in terms of the volume fraction of the solids. So, here if Cv is the volume fraction of the solids, then this slurry density or the mixture density is calculated in this form, where rho s is the density of the solid particles or the material and rho f is the density of the fluid, and as I said, in this case the liquid phase. So, based on this expression we can find out that what is the mixture density. In terms of say mass fraction instead of this volume fraction, we can also obtain such expression, which would look like in this form. Where this Cw stands for the mass fractions of the particulate solid. So, by this way also we can find out what is the mixture density. So, either for a slurry, either we can know what is the mass fraction of the particulates or the volume fraction of the particulates. Based on any of this information, we can obtain its mixture density. Now, when this slurry flows, it flows in different regimes depending on the feed rate or the superficial velocity. Now, also this slurry, we can understand these solid particles are basically immiscible, that are suspended in the liquid phase, and it should ideally be remain suspended while it flows, which means there are chances that depending on the sizes of these particles, since these are immiscible, if you remember our concept on its falling time to the bottom surface of a pipe to the travel path or the travel distance that it travels in between that time. Okay. So, in this relative sense, if the particle size is big enough, or say it is highly concentrated, or say has a certain concentration, and the hindered settling happens before it moves to its destination, then those particles will settle. So, which means the slurry can be transported in different flow regimes. Ideally, if this slurry is meant for transportation, then these particles should be suspended all the time, so that it can be efficiently carried till its destination. So, based on this idea or this observation, this slurry transport has been categorized or has been divided in 3 flow regimes. One is the homogeneous flow, in which there is a uniform distribution of particles over the pipe cross section or say the flow cross section. So, when it flows through the pipe, so this contains the solid particles, the fluid is flowing. So, at a certain cross section, for homogeneous case, if this is the cross sectional view, there should be a uniform distribution of the particles, or say there shouldn't be any concentration gradient in this cross section. If that happens, we typically say this is the homogeneous flow, and then the particles should settle very slowly, and as I said, ideally it should remain in suspension. So, in this category, this kind of slurries are also called the non-settling slurries, because by the time it settles, it reaches its destination. So, that means in the flow region or in the flow path, it is not settling. So, the flow properties in this case are basically dictated by the solids. Its geological properties are dictated by the concentration or the type of the solids. So, this slurries or the slurries that has high concentration and finer particles, say less than 75 micron, in that range, this kind of slurries exhibit this homogeneous flow behavior. Now, with a fixed particle or a given particle size, if we increase its concentration, the solids concentration, the flow tends to be homogeneous in nature. It becomes more homogeneous suspension. Examples of this homogeneous flow or the homogeneous flow regime that behave in this homogeneous flow is the sewage sludge, drilling muds, detergent slurries, fine coal slurries, paper pulp suspension. These typically doesn't not settle quickly, the particles, and it flows along with the bulk motion of the fluid or the liquid, and typically there is a uniform distribution of the particle all over its cross section. So, these are the characteristics of homogeneous flow. In case of heterogeneous flow, on the unlike this homogeneous case, there would be a pronounced concentration gradient across the flow cross section, which in homogeneous case was supposed to be uniform cross section, uniform gradient, or there shouldn't be any gradient, there is a uniform distribution. In this case, there is a pronounced concentration gradient across the flow area. Now, it contains fine fully suspended particles with significant concentration gradients as well as rapidly settling large particles, because now we understand that why we have covered this settling phenomena before we came to this flow behavior, because we know the terminal settling velocities, it is its dependency on the particle diameter. So, if the particle size increases, it rapidly falls. Now, this heterogeneous flow contains this both range of particles. One is fully suspended very fine particles, but it will have a significant concentration gradient along the flow area or pipe cross section, as well as it will have rapidly settling large particles. So, this in this kind of flow regime or this kind of flow shows the tendency of particle settling at the bottom of the pipe or the bottom of the surface or the bottom of the conveying system. So, in this case, it has been seen there is insignificant influence of the particle on the bulk property of the flow, unlike the homogeneous case where its geology was depending on the solids. but here the solids doesn't have much influence on the flow properties of this heterogeneous flow. The examples are of this case is the slurries consisting coarse coal, potash, rocks. So that means size gets bigger and bigger, it tries to settle at the bottom of the conveying system. So this is the homogeneous regime, then the heterogeneous regime, and then we have saltation regime in slurry transport. So here what happens in this saltation regime, the particle slides, rolls, jumps at the bottom of the pipe, which means the particle has already settled. Some of the particles are settled and fluid stream is flowing. So there is a clear segregation or a clear distinction between the liquid, bulk liquid flow, and there is a moving bed of particulates, and during its motion the particle jumps, rolls and slides along the bottom surface of the pipe. So that means there is accumulation of particles and formation of a moving bed at the bottom portion of the conveying equipment or the conveying system. This regime we call the saltation regime in slurry transport. So if we look at the flow regime map, so that map would look like something similar to this schematic that is shown here. Now in this case, this schematic also important from the point of pressure drop calculation, because this is one of the prime concern in moving the slurry from one place to other. This is the mechanical energy requirement that is dictated by this pressure drop that will happen when this transport is taking place. So such kind of information can be obtained from the log plot of the pressure gradient and the slurry transport velocity or the superficial slurry velocity, which is again the volumetric flow rate divided by the cross sectional area of flow is the superficial slurry velocity. So in this case, the two lines are shown, one for the settling slurries and other for the non-settling slurry. So by now we know the settling slurry means when the particles settles at the bottom. So in such case, say the flow is happening. Now we start from a say at a high velocity. Say at first we understand from this direction that we have had a very high velocity and the slurry was moving. There was a liquid bulk motion of the liquid, and at the bottom there is a moving bed of the settled particles. That amount of the particles at the bottom would be lesser in this case because of its high velocity, bulk velocity of the liquid. Now for that we need a critical velocity called the standard velocity. If the velocity is beyond or above say the higher than the standard velocity, then this settling slurry behaves as if a homogeneous flow. That means this is at a very high velocity, all the settled particles basically again get suspended due to its chaotic motion, and the cross section would apparently look like that it has an even distribution of the solid particles. So the point is that this relative concept that the time it reaches a certain distance and the time it takes to settle, within that time if it reaches a certain distance, that means it can remain suspended for a longer time, and that happens here. Once we increase the bulk velocity to a greater extent, then the settling time in which it was falling, by that time it would travel a long distance. With that concept, it creates a homogeneous mixture or homogeneous flow. But below this standard velocity, there is the evidence of heterogeneous flow, which means again here there is a concentration gradient across the cross section. The particle settles rapidly. it creates a layer of particles, and if we further go below another value called the critical deposition velocity, the particles deposits basically. So, this is the scenario, say the particles nearer to the bottom surface and there is a sufficient concentration gradient along this surface. So, if we go below a certain velocity which is called the critical deposition velocity, these particles basically settles, and once it settles we have seen the saltation regime. That means, now these particles along as it flows, it rolls, it slips, it jumps over one another. So, which means in order to keep the particles suspended, we require critical deposition velocity and we have to operate above of this velocity or higher than this velocity. Then the particles are not deposited on the surface, it is flowing with the bulk fluid, but with a concentration gradient across the cross sectional area. At a further higher velocity, which is called the standard velocity, above which we have the settling slurries behaving as homogeneous slurry, homogeneous flow. In case of non-settling slurry, there is no point of discussing any saltation regime because it is not settling. So, there is a two clear flow regime we observed, one is the laminar flow, the other one is the turbulent regime. Now, in both the cases we can see that the pressure drop usually increases as we increase the superficial velocity. But in the case of settling slurries, what happens once we reach the saltation regime, the pressure drop further increases. If we go beyond or say below the critical deposition velocity, the pressure drop in the settling cases increases because the particles has settled at the bottom. Now it requires higher pressure drop for its movement. It is not further suspended in the fluid cross sectional area. But in case of non-settling slurry, there is a sharp gradient or sharp change in gradient when the flow moves from laminar to turbulent. Such sharp distinction is not observed in case of settling slurries. So, by such graph we can have the pressure drop information and which is basically related with the superficial slurry velocity. And this schematic also depicts the different regimes that is there in case of slurry transport. So, now in order to have a model or to calculate its pressure drop and all other hydrodynamic parameter, we need certain rheological models, like in fluid dynamics we have seen there are several viscosity models are there. So, here typically all the models for the rheology this slurry transport are based on the continuum fluid models, and that actually is valid when the solid particle settles very slowly, or say it remains suspended till it reaches its destination or for a longer time. Homogeneous slurry is one of the extreme or the limiting factor of this slurry transport, because in this case all the particles are basically suspended and never settles. Basically it has a uniform cross section as well, uniform concentration grade. that doesn't change in the direction of the flow as well. So, in this case, Newtonian and non-Newtonian flow behaviors can be observed, and several slurries are there which exhibits the Newtonian as well as the non-Newtonian flow behavior. But mostly the slurries exhibit non-Newtonian behavior. That also depends on the solids concentration in the slurry. So, in the higher solids concentration, that means when the slurry is homogeneous, I mean, because for a given particle size, as we increase the concentration, it becomes more homogeneous. So, on that note, when we try to model or when we try to estimate this kind of slurry, we typically assume that this is a single phase flow with the mixture properties, and its characteristics are completely different from the original liquid. Original liquid means when it was without any solid particles. Now, we have seen in Newtonian fluids, in laminar flow, the expression between the shear stress and the shear rate, which gives us the Newton's law of viscosity. Now, the similar concept also applies here if it behaves as Newtonian slurry. Now, in this case, that means we have a linear relation between the shear stress and the shear rate, and if we plot this graph of shear stress and shear rate, shear stress or the strain rate, the slope of the line gives us the viscosity of this slurry. So, in this case, as we increase the strain, the shear rate shear stress increases. Now, in dilute suspensions of fine particles, this kind of slurry basically behaves as Newtonian fluid, and in order to obtain its viscosity, there is a theoretical relation proposed by Einstein, which says that for lower than 2% of the volume fraction of the solids in a slurry which contains uniform spherical particles, the viscosity can be obtained from Einstein relation, which is given as this expression, where this mu m is the slurry viscosity and mu f is the single phase fluid viscosity, that means the original liquid viscosity, and Cv stands for the volume fraction of the solids. This ratio of mu m and mu f is called the relative viscosity. So, it specifically applies in the range when there is a very dilute suspension, the solids concentration is lesser than 2% volume concentration, and it consists of uniform spherical particles. But in most of the cases, these criteria are not satisfied. So, in case of non-spherical particles and of higher concentration, there has been a significant deviation from the predictions by this expression of the viscosities of this mixture viscosity. So, basically what we have covered till now is that we have introduced the slurry transport, its different flow regime, and how the behavior of this slurry can be estimated, firstly by estimating its viscosity. And the rheological model, the governing equations typically assumes that the slurry is continuum. So, we will be discussing this further in our next class and in detail. Till then, I thank you for your attention and we will see you continuing with this discussion in the next class. Thank you.